Swayam Prabha. Digital India. Educated India.
We have come to the last lecture of the course. We will quickly recapitulate the course coverage in this lecture. We will go week by week. If you recall, the first 6 weeks of the course covered theoretical aspects of aerodynamics. In the week 1, we looked at 3 major components or approaches in modern aerodynamic studies, comprising of the theoretical, which comprises of again analytical or semi-analytical approaches, experimental approach and numerical approach, which we often call as computational fluid dynamics or CFD. And these different approaches are meant to complement and validate each other while you study an aerodynamic problem. We introduced the concept of standard atmosphere, and the detailing was done in terms of different altitudes like geometric, absolute and geopotential altitudes, temperature distribution at different heights based on isothermal and gradient regions, use of the equation of state to obtain pressure and density variation, and then important concepts related to aerodynamic flows comprising of pressure, density, temperature, flow velocity, skin friction. There was more in week 1. We looked at the 4 very important forces which act on an aircraft when it is in flight, comprising of the weight, which includes the structural and component weights, the payload, the lift, which is caused due to the floor turning around the lifting surfaces of the aircraft, thrust. We looked at the thrust equation for air breathing engines, and then drag force, comprising of different components again, comprising of skin friction drag, pressure drag, induced drag, wave drag, and we know that these forces balance each other in steady level flight. So, this diagram at the right top corner, we would recall that we talk about the balance of these forces through this diagram. We learnt about integration of pressure and shear stresses to obtain forces and moments which act on the airfoil. And then we looked at the relation between normal force, axial force, lift force and drag force as a function of angle of attack alpha. So, we recall these very important equations connecting the forces. Then we learnt about how to non-dimensionalize forces and moments, and in the process we introduced many coefficients like pressure and skin friction coefficient, force coefficients comprising of normal, axial, lift and drag forces, and then different components of moments. In all, we discussed about 3 components of forces and 3 components of moments, and we learnt about the nomenclature, how we indicate it for a 2D and a 3D body, and then we learnt about the external shapes and surfaces on an aircraft which help to maneuver and execute the mission of an aircraft. These were the important concepts that we discussed in the week 1, where we were introduced to the important aspects of the course, and then we moved on to more detailing on certain other aspects of the course, where we talked about the flow field from an Eulerian and Lagrangian perspective, where in Eulerian perspective we learnt about the control volume approach, and when we looked at Lagrangian perspective, we looked at how we could follow the fluid particles as they move through the flow field. Thereby, we learnt about fluid trajectories, we learnt about the concepts of streamlines, path lines and streak lines, and then we learnt about the kinematics of the flow. There were many aspects that we discussed about, like angular velocity, curl of the velocity vector, the vorticity, strain of a fluid element, rotational and irrotational character of the flow, and then we also learned where rotationality occurs in flow fields, like we remember it occurs within a boundary layer. We learned about circulation and vorticity as well as velocity potential. Revision of mathematical concepts was also taken up. We discussed about gradient, divergence, line, surface and volume integrals, and as they apply to open and closed surfaces. We discussed about the very important Stokes divergence and gradient theorems, which are very widely used in fluid dynamics. Then we moved on to the very important conservation equations encompassing mass, momentum and energy, and we learned to derive them and apply them both in integral and differential forms. So, these were the main things we did in week 2. Then we moved on to week 3, where we talked about inviscid and viscous flows. We discussed about potential flow, which basically connects with the inviscid nature of the flow, and boundary layer flows, which of course belong to viscous flows. Then we learned to distinguish between compressible and incompressible flow, laminar and turbulent flow. Some more topics and concepts that we discussed include fluid friction that occurs due to the viscosity of the fluid and also manifests when velocity gradients are there, the slip and no slip conditions as they apply to inviscid and viscous flows respectively, different kinds of pressure gradient situations like favorable, adverse and neutral pressure gradients, how adverse pressure gradient can affect the flow and induce flow separation. Thereby we discussed about situations where the flow can remain attached or where it can get separated, and that's a very major issue in aerodynamics because that has a direct connection of with the aerodynamic efficiency of the lifting configuration. We learned about a very important concept of substantial derivative related to the unsteady and advective effects in the flow, which essentially connects with the fluid element acceleration. We learned about the very important non-dimensional number, the Reynolds number, and its existence in the Navier-Stokes equations, which deal with the viscous flow. We learned about Euler equations, which can be applied to inviscid situations, and to Bernoulli's equation, which is a further simplified form of the Euler equations. We learned how to apply it, where to apply it. Then we looked out at the compressibility of the fluid medium, and we realized that there could be different ways to assess it. Then we looked at pitot-static tube as a possible experimental tool for velocity measurements in fluid fields. We got introduced to Laplace equation, which is used for representing potential flows, and we also looked at boundary layer flows with a little introduction to boundary layer equations, the concept of displacement thickness, the concept of assessing skin friction using the boundary layer equations, etc. We thereby kept on building a lot of tools, a lot of exposure and enrichment in the different aspects of aerodynamics. Then we spent quite some time in week 4 on airfoil geometry and its applications. When we discussed about airfoil geometry, we looked at chord line, camber line, thickness distribution, the leading and trailing edges of an airfoil. We also learnt about different possible geometries which are existing in the present world through a lot of airfoil series which are existing, not only the NACA series but also many other series which have been developed over the ages. We learnt about pressure distribution on an airfoil as a function of angle of attack. We learnt about the very important concept of center of pressure, and then we looked at airfoil characteristics, which basically come through plots like CL alpha, CLCD, CM alpha, etc. We looked at symmetric and cambered airfoil, the forces and moments as they occur on an airfoil, a very important concept of aerodynamic center, and then we looked at elementary flows, which are nothing but solutions of Laplace equation which are very important ingredients to tackle potential flow past airfoil. So, elementary flows like doublet, point vortex, vortex sheet, etc. were developed, and they were applied to lifting and non-lifting flow analysis. We learnt about Kutta-Joukowski's theorem, which helps us to assess the lift per unit span on a lifting surface. We learnt about the Kutta condition, which is to be applied at the trailing edge of airfoils. We learnt about the Kelvin's circulation theorem, and then we developed the thin airfoil theory, which is a very important tool in analyzing potential flow past airfoils. We applied the results of thin airfoil theory to symmetric and cambered airfoils. We learnt about flow separation and stall, how they depend on the airfoil shape and its orientation, and we mostly spent time on streamlined bodies in this week, but we also looked briefly at bluff bodies and how the behavior, the aerodynamic behavior of streamlined bodies compare with those of bluff bodies. We moved on in week 5 to look at concepts associated with finite wing geometry, that means wings which have finite span, and we compared the characteristics between airfoil and finite wing aerodynamics. We looked at delta wings at high angle of attack. We looked at unsteady effects in airfoils and wings. Flow features around finite wings was studied in detail. Formation of wingtip vortices in a finite aspect ratio wing was understood. The associated downwash was understood. And then we looked at geometric angle of attack, induced angle of attack, how they are connected. The effective angle of attack has a connection with these two angles. We looked at induced drag, which is essentially a form of the pressure drag, and different types of drag was revisited in the form of skin friction, pressure or profile drag, wave drag, and how they apply on 2D and 3D bodies. We looked at vortex filament and the Biot-Savart law, which was introduced in this chapter in the context of finite wings, and based on that the Prandtl lifting line theory was understood. We saw the concept of horseshoe vortex, which comprises of a bounded and a trailing vortex pair, and in this connection we looked at the Helmholtz theorems. Applying the Prandtl's lifting line theory, we looked at elliptic and general lift distribution and how it works out on a finite wing. We looked at aspect ratio effects. We looked at swept and unswept wings, tapered and untapered wings, and we discussed about the induced drag factor and its variation with taper ratio of the wing. Next, we moved on to delta wings, and we looked at the tip vortex roll up and vortex induced lift, which keeps it aerodynamically efficient up to very large angles of attack compared to airfoil aerodynamics. Then how vortex breakdown occurs at high angle of attack and leads to reduction of lift and increase in stall over the delta wing. But we saw that the stalling is rather smooth, it is not a very abrupt stall that occurs. Then we looked briefly at unsteady aerodynamic effects in flapping wings of birds and man-made flappers. This is what we covered in week number 5. Then we looked at compressible flows in the subsequent week, where we started by revising aspects of thermodynamics, where we mainly spent time on revisiting first and second laws, and then we moved on to look at how speed of sound can be derived from the relevant equations, the definition of Mach number. We looked at different kinds of pressure waves, both weak and strong. Examples are Mach waves and shock waves. And then we derived the velocity potential equation and looked at its applications mainly in small perturbation problems. Concept of characteristics was discussed, and then we looked at finite compression waves, which encompass shocks as well as expansion waves. We looked at conservation equations as they apply to normal and oblique shock, and in the context of oblique shock we looked at the very important relation of theta beta m, Prandtl-Meyer expansion fan theory was discussed, and once we were comfortable with shocks and expansions, we applied it to the shock expansion theory, which we found to be very, very efficient in predicting the pressure distribution on different geometries applicable to compressible flows like diamond airfoil, for example. Then we discussed about quasi one-dimensional flow through a converging diverging nozzle under different back pressures, assuming that the nozzle was essentially choked. Under-expanded and over-expanded flow was discussed in detail. We looked at area velocity relation, we looked at characteristic Mach number, and then we looked at flow past an airfoil over a range of free stream Mach number, and thereby we discussed about the very important concept of drag divergence Mach number. Finally, we looked at shock tubes, and we also discussed about the very hot thin shock layers in hypersonic flows. So, we spent a lot of time on compressible flows in this week. Then we moved on to the 7th week, where we had 2 weeks of exposure to computational aspects of aerodynamics. We begin by discussing many applications where we were trying to emphasize on how to choose a mathematical model for solving a given problem, and giving importance to the flow physics, we essentially choose such a model. For example, for solving flow past an airfoil, whether we should use the thin airfoil theory or we should go for the potential flow, where we end up solving either Laplace equation or the full velocity potential equation, or should it be Euler equation, or should it be Navier-Stokes equations. It cannot be arbitrary. So, we tried to argue that in what kind of a problem which model fits in. Thereby, assumptions and approximations associated with each model plays a very, very important role. That is what we tried to emphasize. Which aspects of the flow can be modeled and predicted well using a governing equation or a system of governing equations was emphasized. Flow past individual aircraft components and complete aircraft or spacecraft were discussed with many examples in this week. We talked about the different steps of CFD which need to be implemented, like the pre-processing step, solver step, and post-processing step. And then towards the end of the week, we discussed about panel method, which is a tool to model potential flow past bodies, and where we essentially solve Laplace equation using a numerical scheme. Both source panel and vortex panel methods were discussed, which apply to non-lifting and lifting flows respectively. And finally, we discussed about vortex lattice method, which is applicable to finite wings. This was the first week we spent on numerical methods. We moved on to week number 8, where we continued on this aspect. We did mathematical classification of partial differential equations and discussed about real and imaginary characteristics. The concept of characteristics was briefly discussed. We discussed about the relevance of initial and boundary conditions. Two kinds of problems, two categories of problems were discussed, namely equilibrium and marching problems. And then we discussed about the pre-processing step in detail through grid generation, and we introduced the concept of grid indices. Then in the solver step, we discussed about the finite difference method, and then we discussed about aspects of numerical schemes like explicit and implicit formulation, accuracy, stability, where we discussed briefly about CFL criterion, and different kinds of errors like dissipative and dispersive error. Discretization of some linear partial differential equations of the elliptic, parabolic and hyperbolic category was discussed, and then we got into one-dimensional Euler equations, where we treated them in flux vector form. We learnt about the Jacobian matrix, and then we also looked at the wave diagram for one-dimensional Euler equations. We briefly discussed about shock capturing with some examples, and then finally we discussed about the two-dimensional compressible Navier-Stokes equations. We looked at the closure problem, the closure of governing equations by incorporating suitable relations apart from the conservation equations, like equation of state for example. Then we discussed about a numerical scheme which is a predictor corrected time marching solution for compressible laminar flow past a flat plate, and we found that at the leading edge there is a weak shock which is formed due to boundary layer displacement effect. So, the problem was discussed with enough detail so that the students could even venture into writing their own codes. With that, we ended the numerical section of the course and we moved on to the final section, which is the experimental aspects of aerodynamics. We begin by definition of a wind tunnel, which is the heart of experimental aerodynamics. Open and closed circuit wind tunnels, their advantages and disadvantages was discussed, and then we looked at some general purpose as well as special purpose tunnels. Components of a general purpose closed circuit wind tunnel were discussed, and then we looked at concepts of jet power, component and section losses and loss coefficients, test section dynamic pressure, energy ratio of a wind tunnel, and then how we can calculate the power input to the wind tunnel from the axial fan that runs the wind tunnel, and also the optimum running conditions for the fan so that you have an efficient operating point. Then we moved on to discuss components of an intermittent blowdown type supersonic wind tunnel. We discussed about supersonic diffuser and its role in enhancing the tunnel efficiency. We also learned how to size the second throat with respect to the first throat so that the tunnel starts appropriately and a supersonic flow is established in the test section of the tunnel. Components of continuous closed return supersonic wind tunnel were also discussed using a simple sketch, and a simple calculation to work out the power requirements was also done. Finally, we moved on to the concept of similarity, and that is a very important aspect in experimental aerodynamics. We discussed about Buckingham pi theorem for dimensional analysis applicable to wind tunnel experiments, and we discussed about different types of similarities including geometric, kinematic and dynamic similarity, and we ended by discussing briefly about wind tunnel handling and safety issues as it applies to both low speed as well as high speed wind tunnels. This was the first week we spent on experiments. Then we moved on to week 10 where we moved on to different aspects of experiments. We started with the discussion on flow visualization techniques, where we classified them broadly into tracer based methods and density based methods. We discussed about surface flow visualization using oil flow, tuft flow, free surface water flow using hydraulic analogy, and we also discussed that which kind of visualization technique applies to low speeds and which to high speeds. There are certain techniques which apply to both, for example oil flow. Flow field visualization using smoke, dye was discussed in the context of low speed flows, while optical techniques were discussed for high speed flows like Schlieren and shadow graph techniques. Then we discussed about how to prepare model drawings and material specifications for fabrication purposes so that you can actually move on to some practical work in wind tunnel testing. How to do the model mounting. There could be different ways of doing it using sting mounting, strut mounting, or even wall mounting of semi-span models, or even full scale models where you do not have a symmetry plane, where the entire model can be put in the wall of the wind tunnel. Pressure measurement using mechanical devices, where we discussed about details about pressure ports or orifices, pitot-static tube, pitot rake, multi-tube gang manometer using water or low density fluids as working fluids, incline manometer to increase the sensitivity of the measurement at low speeds, boundary layer probe which are specially designed to obtain the velocity profile near the boundary layer, pitot tube in supersonic flow where we use the Rayleigh pitot tube formula to obtain the test section Mach number, where mercury manometer is the obvious choice because of high pressure requirements. Then we discussed about drag measurement using two methods. One is by wake survey using a pitot rake, the other was by a direct weighing method, and finally we looked into the conceptual wire balance based spring scales for force balance and moment for force measurement and moment measurement requirements, where all 6 components practically can be measured using such a setup. And then we ended the week by establishing the need for accurate alignment and calibration of balance. In week 11, we discussed about electronic methods of measurement in wind tunnels, where we discussed about variable resistance electronic transducers, gauge factor of such transducers, materials, then Wheatstone bridge arrangements both in summing and differencing circuit, force and moment measurements using strain gauge based balance, electronic pressure sensors and scanners, and we also categorize them as absolute gauge and differential pressure sensors. We discussed about different components of data acquisition systems comprising of the transducer, multiplexers, signal conditioner, analog to digital converter, data card, acquisition and post-processing analysis software, and we finally ended with a lecture on measurement error and uncertainty, which is a very important aspect of all measurements. The final week was spent discussing about particle image velocimetry and little bit about how to perform aerodynamic studies using the available instrumentation in wind tunnels with some examples. In the PIV sections, we discussed about obtaining coherent flow structures using PIV. It is essentially a non-intrusive method and is also a whole field technique where you look at the entire flow field which is illuminated instead of making point wise measurements. For performing it, optical access is necessary at wind tunnel test section. Tracer particles have to be suitably chosen both in terms of materials and sizes, and also their optical scattering properties. They would undergo some kind of velocity lag, but if they are suitably chosen, then that can be minimized and they can very faithfully replicate the fluid motion. PIV measurement is based on particle image pattern displacement, and therefore using suitable tracers is a must. Then to eliminate the tracer laden flow, laser light source is used. We discussed about them. We discussed about how to choose the duration of illumination and time in between two successive light pulses, their significance, the light sheet optics, camera, spatial cross correlation analysis, the significance of a synchronizer, and then we ended the discussion with looking at flapping wing PIV and load cell setup description, and then moved on to low speed wind tunnel calibration, fan RPM versus test section velocity, angularity, axial pressure gradient measurement, turbulence intensity, before we started discussing about performing experiments, because we tried to establish the need of calibrating a wind tunnel before we perform experiments. Then we discussed about some very simple experiments like trying to obtain pressure distribution on a cylinder or an airfoil using pitot tube and manometer, that is by mechanical means, or to obtain forces on a wing using electronic balance and pressure measurement by using a scanner. So that was by using the electronic measurement method. And then different methods of obtaining test section Mach number in an intermittent blowdown time supersonic wind tunnel was discussed at the end. So with that, we ended the week 12 of the course. Finally, in this lecture, we were briefly recapitulating the week-wise topics that we discussed in this course. We tried to assess whether a reasonably balanced introductory exposure could be imparted to the theoretical, computational and experimental aspects of aerodynamics, and whether we could cover that in this course. I hope this course content has been useful for you and you have enjoyed it thoroughly. Thank you.